So actually, the most useful combination of functions is often what's called a composition of functions. So instead of adding two functions, subtracting them, multiplying, dividing them, what we're going to do now is we're going to take one and put one into the other. So how do we do this? Well, let's have f and g be functions again, and here are the composite functions. So again, notation. This f little circle g, that's the composition. So that's said in some different ways. F of g, f composed with g. So I'll probably just say f of g. F of g of x is computed as f of g of x. And g of f of x is g of f of x. All right, so what we're doing in these is we're taking, so if I think about this one, think about f of g of x. What happens is I take some x value and I put it in and I evaluate g of x. So now I have a new number in there. I have what g of x is for some x. That's what's going into f. So I take that whole result and then it goes into f and I get my result. So instead of doing them where I put something into f and I put the same thing into g and do something with it like we were, now they're going in sequence. One goes into one function first, you calculate the result, and that result goes into the other one. All right. So how does this affect domain? Well, think about it this way. The domain of the composite function, first, let's just look at f of g of x, is a set of all real numbers such that x is in the domain of g because it has to go into g first, and then g of x, whatever comes out, has to be in the domain of f. So again, because g of x, its result is going into f, not x itself, I have to know what comes out of g to restrict what goes into f. So let's see how this works with some examples. All right, let's take f of x equals x plus 2, and g of x is 1 over x. All right, so the domain here, let's look at domains before we get to the rest. Well, x plus 2, that has the domain of all real numbers. There's no restrictions there. G of x, its domain, well, we have the x in the denominator in this rational function here. So that's going to be all real numbers except x equals 0, because I can't let x be 0 there. Okay, so now let's build the functions we were talking about. F of g of x. Well, again, that's f of g of x. That's g of x going into f. So how would we look at that? Well, think about it. That's f of, and so what would g of x be when we put x in? Well, that's what the function tells me. G of x is 1 over x. So now I would do f to 1 over x. So I'd be plugging in 1 over x in the function f of x. Well, that means that 1 over x is going to replace x. So it would be 1 over x plus 2. Okay, then let's look at what you would get from g of f of x. Well, that's g of f of x. So that means I'm going to be doing g to whatever comes out of f of x. But what comes out of f of x is x plus 2. All right, when you put an x into f, you get out x plus 2. So that's what's going to go into g. Now, what does g do? G takes whatever goes in and does 1 over it. So g of x plus 2 is actually 1 over the whole x plus 2. Now notice, they're not the same. So the compositions in different orders are not necessarily the same. All right, so let's talk domains now, because that's a little trickier here with the composite functions. Basically, I can do it in sequence here. I have to think about what's happening. So first, a number is going in to G. So I consider the restrictions there. So if I want a number to go into G, its domain is all real numbers except x equals 0. So that is a first restriction. Then, when it comes out of G, it goes into F. But F allows everything. So there's no further restriction. So the only restriction I have is when it originally went into G. And so my domain would be all real numbers except x equals 0. Right. Now, what about for the composition G of f of x? Well, let's be careful. Again, first it has to go into F, but F takes everything, so no restriction there. Then it comes out of F and goes into G, but G can't take anything that's going to put a 0 in the denominator. In other words, I can't put 0 into G because it would give me a 0 in the denominator. So in this case, putting in 0 into G, you would put 0 into G when x plus 2 is 0, or in other words, when x is negative 2. So negative 2 is the point that is the x value that can't go in. So it can't go into the whole composite function because it would give 0 to go into G, which is no good. So here now, the domain is all real numbers except x equals negative 2. All right. How about some calculations here? All right, so how would we do f of g of 2 and g of f of 2? All right. Well, f of g of 2 means you do f of g of 2. Means I would calculate g of 2 first. But g of 2, so g of 2 is 1 over 2, because when I put something into g, I do 1 over it. So this would be 1 over, so g, this comes out to be f of 1/2. F says take whatever is inputted and add 2 to it, because that's what f was here. So f of 1/2 is 1/2 plus 2. And that's 1/2 plus 4/2. That's 5/2. Now what about g of f of 2? G of f of 2. But f of 2, when you do f of 2, you take 2 and add 2 to it, so you get 4. So we'd be doing g of 4, which that says, g says take what goes in and put 1 over it. So that's 1/4. So there we go. Notice, not necessarily the same. And that's going to be true of most composite functions, that when you do them one way is not necessarily the same as when you compose them the other way.